This is problem 1 of Worksheet 2 for Module 1 in the book Problem Solving Guide for Electromagnetism and Optics. Involves 2-point charges. Minus 3 nanocoulomb charge at minus 2 centimeters plus 1 centimeter, and a plus 2 nanocoulomb charge at 1 centimeter, 1 centimeter. We want to know the electric field at the origin. So to get the electric field at the origin, we have to focus on the field produced by these two charges at the origin. If we put a test positive charge at the origin, the minus 2 nanocoulomb charge is going to push it. Like charges repel, so we need a vector directly away from the plus 2 nanocoulomb charge at the origin, and there it is. The minus 3 nanocoulomb charge will attract an imaginary positive charge at the origin, so we need a vector towards it. It's going to be somewhat smaller because the 3 nanocoulomb charge is further from the origin than the plus 2. So now we have to calculate the lengths, the magnitudes of those electric field vectors. And to do that, we're going to use E as kq over r squared. The problem is we don't know r. We have to calculate r. What's the distance between the point at which we're calculating the field and the charge? We can use the Pythagorean theorem. The plus 2 nanocoulomb charge is 1 centimeter in the x, 1 centimeter in the y. So that's the square root of 2 centimeters, 1.414 centimeters, and we convert that to meters. The 3 nanocoulomb charge, 1 centimeter squared plus 2 centimeters squared, square root, 2.236 centimeters, which is 0.02236 meters. We converted it to meters because this constant K is Newton meters squared per coulomb squared. So to get the meters to cancel out, we need to put the distances in the bottom in units of meters. So now we're ready to calculate the field. kq over r squared, we know those. We know everything. There's K, there's Q. We converted it to coulombs because K has a coulombs in it. So 2 nanocoulombs is 2 times 10 to the minus 9th coulombs. There's the distance, and we get 89,900 newtons per coulomb. That's the length of this electric field vector, the one produced by the plus 2 nanocoulomb charge. The field at the origin produced by the minus 3, kq over r squared. Note, I'm not putting in the signs. I know the direction. I don't need the negative sign to tell me whether it's attracting or repelling. I know the field's going to be this way. All I'm doing is calculating the magnitude. That's the absolute value of that vector. 53,940 is the length of that vector. So now we have to get the vector sum of those two electric field vectors. And it's a good idea to say, where's it going to be? It's going to be something like that. The field should be something like that. If I get something very different from that, I must have did something wrong with the algebra or something. So we need to get the components. To get the components along the x and y axis, we need to get the angles they make with the axis. This one's 45. It's a 45, 45, 90 triangle, 1, 1, square root of 2. Put that angle in. And we need to use arctangent for this angle. The opposite side is 1 centimeter, the adjacent side is 2 centimeters, 26.565 degrees. Now we have the angles, we can get the components with trigonometry. The field in the x direction is the x component of this guy and the x component of that guy, and they're both negative. So 89,900 cosine 45 degrees. That's that length. 53,940 newtons per coulomb cosine, that's this length. And they're both in the negative direction, that's 111,800. Now let's do the y. The one from the 3 nanocoulomb is up, so they're opposite directions because the plus 2 nanocoulomb is down. So we have negative 89,900 newtons per coulomb sine 45 plus 53,940 sine 26.565, that's minus 39,000. Still down. So now we can use a Pythagorean theorem to get the magnitude of the electric field. E sub x squared plus E sub y squared square root. And the answer is 119,000 newtons every coulomb. That's the magnitude. To get the angle, we can use arctangent. The vertical component is 39,004, and the horizontal component is 111.8, and that's 19 degrees, and we know it's below the negative x-axis. So we have the answer. It's 119,000 newtons per coulomb at 19 degrees below the negative x-axis, so we can replace these two electric field vectors with one electric field vector, the net electric field vector, and there it is. 119,000 newtons per coulomb, 90 degrees below the negative x-axis. That's it.